All right, welcome to another Physical Sciences Machine Learning Nexus seminar series talk. Today we'll have Professor Eric Mjolsness talk about the symbolic neural networks. Professor Mjolsness got his bachelor's in physics and mathematics at Washington University and got his PhD in neural networks from Caltech in the mid-80s. He led many scientific projects at UC San Diego, Yale, the Jet Propulsion Lab, and UC Irvine since the early 2000s. So this means several decades, at least 4, of work on mathematics and artificial intelligence. So his current research interest is in mathematical artificial intelligence, machine learning for multiscale science, where the emphasis is high-level symbolic representation of spatial models which result in morphodynamics, and is a significant challenge for mathematical and computational frameworks to reconcile different scales, which is significant potential for the use of machine learning neural networks in physical sciences. So we're pretty excited with not only his talk, but with involving Professor Mjolsness in the PSML Nexus in the future. In fact, there is an upcoming event in October 26, if I recall it right, that is focused on physical sciences and machine learning. So without further ado, please welcome Professor Mjolsness.
Learned and reproducing kinetic energy profiles as a function of depth nicely with a neural network out of sample, of course. You change the conditions and then you run it and see how you did. And this was presented, a lot of work like this was presented at the workshops that Los Alamos National Lab presented over the last few years. On the right side, there is a gene regulation network picture, which is one of the little systems that I've been working on, well, I had worked on previously. John Reinitz and Dave Sharp were my collaborators back then when we learned how to learn connection strength parameters in a gene regulation network and fit it to data. So the idea is dynamical models, you can build some kind of learnability into the models that allows it to either fit to data or fit to big simulations that are in turn fit to data. Well, I mentioned that there's an explosion right now, and here's just a little sampling of some of the papers. If for some reason you can't squint and read all that stuff right away, I think we're going to be making the slides available with a couple of slides like this, and certainly if not, you can always email me for them. This is just some excerpt from a literature survey I did around January, but it's already out of date. There are important things since then. Well, going way back in the history, what is this symbolic versus numeric business in artificial intelligence? So I would go right back to Principia Mathematica in 1910 by Russell and Whitehead, showing that mathematics can be turned into a formal system. And that was even before Turing's definition of what computing is, but the verification could be done in a computational way, in a mechanical way. And they had to invent many great things in order to do that. People sometimes say Principia Mathematica was a failure. I don't think it was at all. They invented the ramified theory of types to get around all the paradoxes that Russell had found, and that will make an appearance later. But the ball got rolling in 1956 Summer Conference on Artificial Intelligence, and one of the talks presented there was The Logic Theorist by Simon Shaw and Newell, which could do a better job of solving Principia Mathematica problem 2.85 than Principia Mathematica did. Found a better proof, and Russell agreed apparently it was a better proof. And of course, the ball got rolling from there. There was a series, the era in the 1970s of expert systems, rule-based expert systems, but also computer algebra got going with Maxima. And then various other developments in programming, high-level programming that weren't called AI, but I think are terrifically relevant. Well, on the other side, it's sort of in parallel with all this. Neural networks also had a prehistory, starting with McCulloch and Pitts in 1943. They defined their model of real neurons. Frank Rosenblatt, 1958, announced, computers that can think to the world, and he wasn't the only one. Bernie Woodrow, and then interest in this was cooled off a bit by Minsky's perceptrons book, but that was really overinterpreted. He proved a theorem that said with one layer of neural net of perceptron you couldn't do some stuff, but Minsky and Papert in their book pointed out that many layers might still be able to do it, and they can. So back and forth between the 70s, expert systems, 1980s, when I got involved, neural networks were exciting. 1980s also was a time of AI winter for symbolic methods. And then, of course, the last couple of decades have witnessed a huge renaissance in neural network side techniques generally, with all these buzzwords that you've seen, and most recently being applied to physical science and to scientific simulation generally. I think the symbolic side is also making progress, just not attracting the billions of dollars. Automatic theorem verification, open computer algebra, improvements in type theory, probabilistic programming, differential programming, and so forth. And there's going to be kind of a merger going on. Then I'm going to suggest some ways of doing that fruitfully. So these were rivals, and they're much more rivalrous than they are in physical science, theory plus computation, analytic theory plus computation, but now they can, I think, be brought together fruitfully. So here's a kind of a picture of how that might look. If you could get numerical AI and machine learning and symbolic AI to be two different ways of looking at the multiscale stack of different kinds of models that are in principle related to each other by scale change, then I think that would be very powerful. But of course, we need to know how to express all this stuff. And the powerful ideas in applied mathematics are only sort of indirectly learned in any kind of machine learning network, whereas you can kind of say what you mean if you're doing it symbolically. So here are some directions that I hope to give a little taste for that we've been working on. One is machine learning for model reduction, so changing scale in this diagram over here. Point over here, these scale changes at the sort of statistical physics level in particular stochastic reaction fusion systems. And the name of our core scale model is dynamic Boltzmann distributions. Then some graph neural networks are a very current topic with a lot of progress, and we have a variety of graph neural networks that brings in the ideas of multi-grid methods, and we're applying that to, Corey Scott is applying that to some model reduction in molecular dynamics. And then, on to higher levels of expressive power for complex systems like the dynamic cytoskeleton inside of a cell, and then more sort of modeling language and symbolic kind of ideas at the end. So the first connection then is machine learning for model reduction, incorporating statistical mechanics knowledge, particularly applied to, so far, to stochastic reaction fusion systems. And this is with Oliver Oliver Ernst at the Salk, along with the other Salk people that I mentioned. And their problems in Terry Sinofsky's lab are largely focused on the synapse, the multiple scales of dynamics that happens inside of a synapse and inside of their simulators for the M-cell simulator for what happens in a synapse as it learns. And you know, so we need a framework for relating dynamics at different scales. And here's what we have in mind. You'll have at the fine scale some kind of non-equilibrium stat mech system described ultimately by the master equation. Here the W will be the operator for that sums up reactions and diffusions. The semantics of the reactions is that given the reactions, you know W and you know how to evolve the fine scale system forward in time. So semantics is going to be a formal map called psi, capital Psi, that takes you from a reaction network to a W and to something you can simulate on the computer. On the other hand, we have a model reduction, that's script R here, that's going to take us to a coarse scale system that I can describe here. It looks a lot like a Boltzmann distribution, even though this is not equilibrium stat mech. It is non-equilibrium stat mech in the, you know, the sheep's clothing of equilibrium stat mech, with the coupling constants being functions of time in some way to be determined. So that's the non-spatial version, and we applied that a few years ago with some of the same collaborators, but also Todd Johnson, and to a complex reaction network that occurs as part of the signal transduction happening in a synapse. So when calcium comes in, that may be part of a signal transduction cascade having to do with learning. Well, it is. And so we took this previously published model and expressed it in terms of reaction arrows with molecule names. And the molecule names have some extra parameters attached, like CAM kinase 2 can tell you how many calmodulins are attached to it, and therefore how many phosphate groups are hanging around. Calmodulin can tell you how many phosphate groups there are at the, not phosphate, how many calcium ions are bound at each end, the two ends. This whole thing can undergo a binding reaction. So you get one less free CAM kinase 2 and one more CAM kinase that knows how many calcium ions are bound to it. And so on. You get a dozen rules like this. It's a vast simplification of the full model, which if you write them out without parameters would be about 1,000 reactions. And so that's the fine scale model, 1,000 reactions with a stochastic simulator that would be something like the Gillespie algorithm. And here's our coarse scale model. It is something like an Ising model. You have these binary variables that in circles that tell you what's bound to what, yes or no, and the interactions, the coupling constants are given by these hexagons that are either pairwise or triple interactions of Boolean variables. And so the problem is to put dynamics, not only numbers, but also dynamics on these hexagons. And so we did that a few years ago by starting with fine scale, the fine scale master equation description. It's written out here for mass action chemical reactions, and approximate it with this time varying version of a Boltzmann distribution. The coupling constants have laws. The laws have to be inferred. You do that by fitting some parameters, and that all worked fairly nicely. So in this little picture of repeating pulses of calcium coming in, the fine scale evolution of parameters is entirely is the red lines that are entirely covered up by the coarse scale model. So basically there's to within the thickness of ink, there's a pretty good match. Well, the more recent work is to try to make a spatial generalization of all that. So the fine scale model in M-cell using big cluster computers can be spatial, involves diffusion and Green's functions for diffusing calcium and so on. What about the coarse scale model? Maybe that should be spatial too. well, then you'll have to make your energy function be a sum of potentials, 1 particle potentials for k equals 1 and 2 particle potentials for k equals 2, that are functions of the positions of the molecules that are being interacted, and also functions of the types of the molecules. So calmodulin and calcium and so on would all have different types. And we'd need to have some laws for the evolution of these new potentials. Again, you're using the intuition from equilibrium StatMech to get close. So this is where our knowledge of physics is coming in to the extent we have it. Well, then it's a matter of formulating an action, something you want to maximize or minimize the KL divergence between the coarse scale and fine scale probability distribution. And there's a little framework for doing that. But what you need, the things that you're going to optimize are the laws by which these potential energies evolve as a function of other potential energies. There should not be a dot there. I forgot to remove that. Okay, so we just do variational calculus and find that the data term is going to be driven by the difference of expectation values between the fine scale system and the coarse scale system, as makes sense. If this is 0, then you don't want to be optimizing anymore, and we just have to sort of parameterize that functional. We did it in various ways, mostly Oliver Ernst's work, and here's an example involving a little reaction network where 2 molecules of the same type can meet, and only one of them walks away alive, and a few other reactions. And basically, for each coupling constant, it becomes a coupling function that depends, whose differential equation, right-hand side of the differential equation, is illustrated here after learning. And initially, nothing matches up, but in the end, first order and second order statistics match up pretty nicely. So to try to wind up this section a little bit, the algorithm for doing this kind of thing, there are several of them, but they all look like the 1980s Boltzmann machine learning algorithm that was sort of on that symbolic versus numeric AI comparison slide. Hinton and Sinofsky published it in 1985 or so. And this can be viewed as a very grown-up version of it, where you have a sleep phase and a wake phase. You evaluate these moments, and you put those into. Now there's the whole problem is a PDE constrained optimization problem. So you have to solve the PDE. You have to use an adjoint, or you can use an adjoint method in order to propagate the constraints, as if you were doing back propagation of error. And it all has to be discretized, put on a computer. And by the way, along the way, we find that hidden units in this representation help a whole lot. Why do they help? Because they control what is the moment closure approximation that you're making. Instead of saying that we're smart enough to figure that out, we let the neural net figure it out, and it does a better job, as we can see by comparing. If we don't have hidden units, here's the error on a log scale, and if we do have hidden units, it's much better. These are those learned left-hand sides of differential equations for the parameters, and this is kind of the demonstration that it learns even in this complicated system. And here's one more step of complexity. We still do not have the learning algorithm that we're really happy with, that we want to throw at the entire Synapse and say, we're going to learn biophysics now. But this is a step into 3 dimensions. And with the Rossler-Williamowski oscillator, which can be chaotic even if it's deterministic. But of course, this is a stochastic version of it. And so you can kind of track a few cycles of oscillation of the means and the covariance statistics of this system. Okay, so so a little bit of moralizing about that is the idea here is we want to build, use machine learning to build model stacks. Your finest scale simulation might be model 0, reality might be model -1, because that model 0 has to be trained on something. And at the very top, you'd like your model to be analysis, some analysis that you understand. So some model that's so simple that it might be an exact solution or something like that. So that you build a stack of model reductions, and each of them can be investigated for their conditions of validity. That's the philosophy. So maybe this is a good moment for me to see if there are any questions. Yeah.
Yeah. Hi, Eric. I have a few questions. Sorry, I was late. My link didn't seem to work. But the variables used in the Boltzmann machine, is there any simple relation between them and the original variables?
Sure. The original variables were coupling constants. They were really constant. You learned a number that told you how two variables are correlated, and we started out by doing that step by step through the simulation results of these M-cell simulations. So you can do it at any moment in time, and then watch the learned parameters and see they were varying kind of smoothly, at least in our highly parameter shared version of model. And so that was the clue that maybe you want to have a differential equation for them and learn the parameters that describe the right-hand side of the differential equation. So it is a straight-up generalization that is actually quite an expensive generalization. You could not have done this in 1985.
Right, but I mean, if you take just one of those, there isn't a direct interpretation of each of those variables in terms of the original ones. It's simply the whole model, right, reproduces.
Well, I guess there is, because you can look at the differential equations and see what the properties are. For example, you could do model selection on that left-hand side and try to decide which coupling constant should be in the right-hand side, which coupling constant should be present or absent in the force law driving each other coupling constant. And so then you get a graph description, and those are usually something human beings can understand, that these things are connected and these things aren't. And likewise, depending on what kind of functions you use, typically we're using some kind of combination of functions that we intuited from analytic solutions of little problems. And so then you have some further structure you can look at. And in fact, the right-hand sides of the differential equations may in fact have a summation structure that's kind of congruent to the summation of different processes in your underlying model. So all of those kinds of structures are in principle there, but I don't know, I think it's probably easier than looking at the billions of weights in AlphaGo or AlphaZero or something like that. It's probably a lot nicer than that, but it's not so nice that we've been able to do it very well yet.
Right. And one other thing is, you had said that you couldn't see the difference between the original model and the new one. But was that like, I mean, had you pick time steps, like is that coarse graining in time? And if you look at on a finer scale, then you see fluctuations about.
Oh, well, there were definitely fluctuations, because the coarse scale model is a statistical model. Then you see fluctuations in the coarse scale model here. You can also see places where it's not exactly covered up. And so you can see, a few percent difference up to.
Oh, yes, I can see them now.
Yeah,
yes,
up to 10 or 20% in the worst case. But just qualitatively, it's coming close a fair fraction of the time.
Yes. Yeah. Okay. Thank you.
Yeah. Okay, so another little exploration is with Corey Scott. We started out looking at, sounds completely different, hierarchical, exponentially growing families of graphs that share some kind of regularity. So for example, hypercubes, and putting them into a structure in which you segregate the different members of that family by their level number and connect adjacent levels up. So we thought that'd be interesting to look at problems that are structured that way, and also networks that are models that are structured that way. So either way, such graph lineages can be grown by graph grammar rules, for example. This triangle replacement is a classic, but you can do it in a lot of other ways. Well, we had some ideas about how you would do that, how you would tell what's this regularity between members of a class. We want to have some kind of idea of distance between graphs that makes adjacent levels within a family look closer than adjacent levels between two different families of graphs. So for that, how would you compare, how would you find the distance between two graphs that are of quite different size? Well, here we're borrowing ideas from algebraic multigrid theory. You have some kind of prolongation matrix, P, that lets you go from coarse scale to fine scale, and then move around in your graph, and then restrict back to, using the transpose, back to coarse scale again, and see if you got close to the coarse scale graph. So two graphs could be related by this equation, and if so, we'd like to say they're close, even though they have very different sides. So they do the same thing as far as their sort of what an ant on the surface of the graph would be doing, or more formally, as far as the diffusion operator of a graph is concerned. So here's a collection of objective functions for P. Probably the simplest one is this one down here, where you have a Laplacian of each graph at each level, and then you prolong one of them on one side of its connection matrix and the other one on the other side of its connection matrix, and then you introduce a little time scaling factor that is to be optimized, minimize that distance, and that would be the distance between two graphs. And in certain circumstances, we could show there's a triangle inequality for that thing. With that framework, we want to invent something that can process graph data. But first, as an aside, there is a very active development of graph neural networks, including multiple faculty who are or have been here at UC Irvine. So there are many options, and this is one of them, to try to bring in the idea of a graph limit or a graph lineage, and the idea of an algebraic multigrid to determine the prolongation between two different levels of graph. So now here is a little molecular dynamics-like problem. Again, this is not something we're ready to use in anger for modeling microtubules, which is what these are, but we're trying to develop the technique. So here is a microtubule clamped at one end and undergoing a beam-like deformation with its potential energy per tubulin monomer, illustrated in color here. So the top and the bottom are stressed and the sides aren't. This model kind of does the right thing. It's not an atomistic model of the tubulin substructure. So, but we're going to take it as fine as ground truth anyway, and try to build a graph processing machine learning model to predict these same energies, and then you can take derivatives to get forces, and you can do simulation. So we're using the LAMPS. Corey Scott is using the LAMPS molecular dynamics simulator. worked hard to get the microtubule to be stable. And then here are his core scale versions, and here's the architecture. So the mappings between the layers are determined by that distance minimization, that you find the best prolongation that, that preserves diffusion operators on these various graphs, including the fine scale graph that is the actual connectivity diagram of the tubulin monomers in the most common structure. And then at each layer, you have a graph convolutional network that predicts things at that level. And in particular, the core scale one can kind of get you the core scale trends, and all of those trends add up in, this is sort of like a UNet and also like a ResNet and like a graph convolutional neural network, but it relies on the prolongation operator, prolongation matrix, and on this idea of a graph lineage that relates similar graphs at different scale. And in some comparisons, we use different kinds of graph, our graph convolution network against a current pretty good one. And on the log scale, we can train so as to generate these potential energies more accurately or as accurately and quicker, or for the same speed much more accurately. So, excuse me. So the idea is we want to create a core scale biomechanical model that then could be put into yet further coarser models of interesting things that are happening in a cytoskeleton that I'll show next. So another moment for any questions about that section. Okay, this is available in a preprint that you can see there. Okay, so now these microtubules or other cytoskeletal fancy polymers in the dynamic cytoskeleton of a cell do all kinds of crazy things. They create, in general, a graph, a dynamic graph that presents interesting problems for how to represent a dynamically changing graph because a differential equation can't do that. Number of variables in your differential equation is fixed, so what can? Well, my claim is that there are a whole lot of dynamical graph problems, spatially embedded dynamical graphs, that we can model at a core scale by using ideas of graph grammars. And so Hartmut Ehrig has worked on this for a long time, and the approach I'll take is similar to operator theory as it's applied in quantum mechanics, except there's not going to be anything quantum about it. Another example of these dynamically changing graphs is cells connected to each other in a living tissue. This is a plant. This is, in fact, the shoot apical meristem of Arabidopsis, which is also my background that you can see behind me, with gene expression patterns. And here's a high-level modeling language. This is a symbolic language for modeling cells and their signal transduction, gene regulation networks, and cell division decisions, and as well as a little bit of biomechanics at a very high level. So we would like to make better models, better high-level models. Here's yet one more example, physics-like examples. There's multiple physics-like examples of dynamic, spatially embedded graphs. This one's a fracture network in an oil field, or it could be at a much finer scale, inside of a single rock as it decides where it's going to break as you're beating up on it, crack propagation and so forth. And so a high-level representation of all those kinds of things is a graph. Our problem is these microtubules in the cortex of a plant cell, which basically decide how the cell is going to reinforce itself, and therefore the future biomechanical properties. And so here's just some videos that show the microtubules moving around inside of a plant pediole cell. You can see they do all kinds of great stuff, including changing the topology of the network. Okay, so why do I say that? We can blow up some frames from there and see, here's a microtubule. Looks like it's going to make a connection there, but no, it suffers catastrophe. It feels better the next day and tries again, and it makes a permanent connection. It changes the topology of this network in this cell. And here's another microtubule that's growing and then retracting. So how do we model this kind of thing? Francois Nedelec has a cytosim simulator that can be persuaded to do some things like this, but you have to program it. So what's the high-level modeling language? Francois would probably say it's cytosim, but I'm looking for something more like those reaction networks that I showed you for modeling the shoot apical meristem. And the idea is, as when two microtubules, when one approaches the side of another, these various things can happen: induced catastrophe, crossover, and zippering or bundling. And here is a graph grammar representation of that. You could have a growing end of a microtubule that turns into an interior node and a growing end. That would be a stochastic jump forward in the size of the length of the microtubule. You could have a microtubule growing and approaching the side of another one and connecting, or undergoing catastrophe, or undergoing crossover, and so on. There are many other possibilities, including a lovely protein called katanin that can induce severing. It can find the microtubule middle and sort of cut it in half, creating two microtubules where there used to be one. Some of those rules are best thought of as differential equations, like the growth but the what happens upon collision is intrinsically discrete. All right. So with that kind of high-level representation in mind, first of all, can you implement this? Right now, we're implementing it by hand in a very scalable framework. I don't know if our code is going to be scalable, but this is the DOE particle simulation code called Cabana, and being advised by Bob Bird at Los Alamos, Eric Medvedev, a new student here, who is growing microtubules in a little field of them, and they do all of these things. And so we think that the code is going to be very, very scalable as a result of that. It requires that you sort of split up space into different cells that can be parallelized differently, and boundaries that have to be thickened up a little bit, because you have to be careful about what happens in boundaries. And then the boundaries have boundaries of lower dimension and so forth. So there's some kind of representation like that. This is just, I have to skip over this proof that Cabana can be very fast on a plasma physics simulation. So the idea is that for spatial models in complex systems, we've got partial differential equations, we've got particle methods, from Ulam invented some of the first of those. But now this is really a different paradigm. It's more like the particle methods, but dynamical graphs may be a fundamentally new category of scientific computation, of simulation. So let's see, operators. Actually, this is slightly out of order. I need to, okay, so let me, so here's a abstract reaction. Parameterized objects in, parameterized objects out. The way you can create an operator that goes in the master equation for this reaction is you can take a product of annihilation operators for the things that go in, and a product of creation operators for the things that go out, just as if you were doing quantum mechanics or quantum field theory, except that all of these are real valued, and they're not Hermitian conjugates with one another, but they obey the same Heisenberg algebra. So that's the the operator point of view on the master equation. If you have a network of reactions, it can be expressed like this. There's a commutation relation for the ladder operators, and given those operators, we can, we get an operator for the master equation that is a sum of terms, sum over all the reactions that look like this, and you can get simulation algorithms out of that by basically splitting it up into a exponentiatable, for example, the diagonal part and the off-diagonal part, using the time-ordered product expansion, and you can rederive the Gillespie stochastic simulation algorithm, but you can take many other variants and get other simulation algorithms as well. And so that's covered in this paper from 2013. What's new here is just to point out that given two such operators for two such reactions, if you want to know whether they commute or not, maybe they don't touch the same molecules, for example, you need to compute their product, and entertainingly, the product of two such operators is a sum of other such operators. So stochastic chemical reaction operators have an algebra. And if you take commutators instead of products, then it has a Lie algebra as well. And so we're used to this kind of thing in theoretical physics as being a potentially nice formalization and very general formalization. But now we want to do graphs. And so now we have to do something like this. Instead of particles in and particles out, we have graphs in and graphs out. We have to create an annihilation. Yes?
Sorry, can I interrupt and just
yes.
The question? I mean, in a chemical reaction, right, all the concentrations are sort of real positive numbers.
Well, here we're taking them to be integers. This is a stochastic.
But there's no phase, right?
Yes, exactly. So that's why I said these operators are missing the square root of -1. They're all real valued. All entries are real, but they satisfy the Heisenberg algebra. And let's see. Unfortunately, I don't have a picture of them, but they're very, very simple. They just the quantum operators have 1 over square root of n down the off diagonals, basically. And here the annihilation has 1 over n down the off diagonal, and 1. The creation operator has 1s down its off diagonal, and so they satisfy the same commutation relation without the square root of -1 in it. And that n, I'm sorry, it's not 1 over n, it's square root of n. It's n. What the n does is it implements the law of mass action for a stochastic chemical reaction. And this is a well-known framework. It's been repeatedly reinvented. And some of the first people to invent it are Doi and Politi. So
okay.
known thing. It's kind of nice. And now we're going to do it for graphs. So we have to create and annihilate not only the nodes, but also the links. And so, for example, here's that treadmilling rule and the end retraction rule. Do they commute? Here's the operator expression for adding an interior node. Here's the operator expression for deleting an interior node from the retreating end. And the commutator is basically up to some constant and up to some things that should never happen if you don't let them happen to begin with. It is this little rule here. So it basically says there's a special case for that if your whole microtubule is only 2 segments long, then it can get renumbered in a way that doesn't really matter. Okay, so let's see. Here's another one, growth versus bundling. So that should have a non-trivial commutation rule because bundling happens when a microtubule grows into another one. And here are all the things that can happen for these 2 rules. This one can happen, but involves an incredible bending of your microtubules. So when we add quantitative parameters to this, this should be discouraged very strongly by bending energy. All right, so the last thing I want to say about this framework is, first of all, I hope it's clear that it can express all of the kind of rules that I showed before, including the differential equation rules. But what is the general commutation relation? What is the algebra? And here it is, after long seeking it for a long time. The product of two such graph grammar rules is a sum of other graph grammar rules that are generated in a sort of combinatorial way by finding outputs of one rule that are to be also found in the input of the other rule in all the edge maximal ways. So you find a collection of nodes that match. You take all the edges that are in common between them and sum over all the ways you can do that. And that will give you the algebra and the Lie operator algebra and the Lie algebra. That's the fundamental theory behind this kind of model. There's an alternative involving category theory that I don't have time to do, but that's where Ehrig and collaborators made their mark. So the last little bit I want to do, so the idea is to build modeling languages that have that kind of fundamental semantics and are very expressive. I call it bio-universal. If you did a model reduction in a language that has these graphs, dynamic graphs in it, and also PDEs and ordinary differential equations, which can all be expressed, then you could stay within the language while you did your model reduction. And that means you can formulate a machine learning problem for doing that. So that's the agenda. Okay, so what about these modeling languages that could incorporate machine learning? Well, I showed you one, the Schudic-Meristem modeling language that had cell division in it, that was embedded, I forgot to say, unfortunately, that was embedded in Mathematica computer algebra system, as have many of our modeling languages. So when you embed your modeling language in a computer algebra system, two things happen. One is your expressive power goes way up because you can write any kind of differential equation you want, or other functions. And the other thing is that it may go more slowly than you'd like. So there's a software engineering problem to get the computer algebra to be the front end, but have a fast back end like Kibana. And I showed you higher level, actually I didn't, in another talk, I had a check mark here. Here I showed you some rewrite rule dynamics that includes graph theory. Now, if you could have other mathematical objects like measure spaces and manifolds and stratified spaces, then the expressive power of your modeling language will go up. Here's the kind of idea for how to do that. We'll have D is the distance measure in a metric space. Sigma is the sigma algebra for a measure space. Mu is the measure that can give you a probability distribution. And there's a symbol for topology and so forth. So from those basic mathematical ideas, if you have them formalized, for example, in a automatic theorem verification system, then you could verify some of these mappings, like the semantics maps or the model reduction map or approximations, or even just verify whether your model can be expressed in my modeling language or vice versa, whether it's possible. So this is, I think, well, for me, at least it's a motivation for trying to express enough applied mathematics of these modeling relevant mathematical objects and the languages that describe processes on them, so that you can partially automate the mappings from one language to another. And my contention is that the automatic theorem verification is becoming strong enough. Here are those maps again: semantics, model reduction, implementation in terms of things that look more restricted, like the a language that describes what Kibana could do for you, and so on. A big one for modelers is translation between one modeling language and another, and people have been going for decades on how to do that. Well, here's a little indication of the improved state of the art in the automatic theorem verification business. Here's a International Mathematics Olympiad question 1, the easy one. A little functional equation, and prove that it has to be that only this form of function would satisfy it. And here is a completely automated proof in Isabelle for doing that. And it involves a whole bunch of Isabelle, please help me heuristics. But by SMT, that by SIMP, those call in big hammers, and one of them is even called sledgehammer. Often, so you can work at a much higher level of theorem of human stating of the theorem and the proof and automatic verification than was possible before. If you don't believe me, go have a look at the archive formal proofs and see some of these great things that people have started to do, like a recapitulation of one of Smale's dynamical systems challenge problems as a PhD thesis. Some graph theory. There's the Isabelle HOL models starting to be for manifolds, measure theory, all the things that I mentioned, metric spaces, logic, ordered fields, all the kinds of things that you might need in order to teach undergraduate mathematics are started sort of checking in. I think I already said this. So then the idea of these putting it all together is that I think the solution to modeling complex systems in general is going to be not a model, but a stack of models. And we need powerful modeling languages that help you do that, to help you verify the reduction relations between the different levels of your stack of models, and that verify that your models are such as will run accurately on my solution software on a big computer and so on. And so there's going to be kind of a zoo of modeling languages, but they can be organized. The rewrite rules give you a way to describe processes. The type theory, a la Bertrand Russell, but a la many improvements in programming language theory since then, including modern versions of type theory, will describe what are the objects, like what is a branched manifold that describes a tissue made out of many cells. They'll pertain to, they'll capture knowledge in different fields, whatever your science is in this kind of hierarchy, whatever parts of mathematics you think are applicable, and whatever computing language is the input language to your solver. And I'm getting a lot of flack now from a gardener out front. I'm sorry, it's slightly distracted by a loud noise that I'm told that people can't hear, but I can sure hear it. So each of these nodes in this diagram is kind of the tip of an iceberg of a whole hierarchy of languages that know more and more about more and more detailed kinds of problems. And we need to be able to build tools to map between these languages and verify the relationships between them. And that's where I think that the automatic theorem verification is going to have a big role that it hasn't had so far. So just to sum up then, I tried to show these 4 different ways to incorporate symbolic knowledge and symbolic manipulation in improvements to machine learning that apply to computational science, computational physics, chemistry, up through biophysics, which is mostly what I talked about. And one answer is yes, you have multiple ways to change scale using machine learning that wouldn't be possible without machine learning. Another is that if you're interested in morphodynamics, change of scale, that introduces a special part of type theory, which is types like manifolds, which can represent an object, but also provide a space in which other objects move. So we have objects which are the types of other objects. And it's kind of unique to morphodynamics. Model stacks are the key data type. Declarative modeling languages with operator algebra semantics can support all this, give it mathematical meaning, turn it into well-defined mathematical problems that can be solved. And in these ways, both symbolic and numerical artificial intelligence can be brought to bear on complex biophysical systems across scales. And since I've got you here for another 30 seconds or so, I'll just advertise these upcoming events. If you're interested, if you're a student and you're interested, then I'm offering a special topics course, class, seminar, I guess you should say, this fall, CS 295. And we're trying to plan now a meeting on a virtual meeting, of course, for October 26th on machine learning for the physical sciences. And Kieran is going to be one of the speakers. Thank you. We haven't quite sent out the announcements yet, but students and generally people in the PSML community are going to be invited to submit poster talks. It'll be just one day, and we're going to try to figure out how to have a nice Zoom poster session that works, but we're still working on how to do that, but there'll be an announcement, I hope. So that really is the end. And I'm ready for any other questions that people might have.
We have one question on the chat.
Okay.
Ryan, you're there. You want to?
Oh yeah, I can ask it. I'm just curious for the graph, sort of the graph reaction modeling. Is
Yes.
Was that limited to 2 dimensions, or is this it can go to any dimensions?
Absolutely. I'm interested in the spatially embedded case, but the notation doesn't limit you at all as to even if it is spatially embedded. So the way you embed spatially is you have the nodes have parameters on them that include vectors of whatever dimension you like. And then you have the rules, pay attention, have their propensity of a rule firing, pay attention to the distance between in that metric space. So for example, you can embed, if your graph doesn't embed nicely into 3 dimensions because you're talking about the internet or something like that, you can embed it in hyperbolic spaces pretty nicely and use that as a metric space. So it's the reason for spatially embedding is to try to introduce some structure so that, what is space for? Space is so everything doesn't happen all in the same place. So to limit the number of interactions that might happen.
I had a question about the operators.
Yes.
Since that formalism in quantum mechanics is designed to take care of complex wave functions, and the quantum effects are often in the amplitudes. I mean, it would seem more natural to me that they would, you'd use sort of density operators rather than amplitudes. So A dagger A type objects rather than just direct creations. It seems like there must be some sort of very, very special rules that must occur when these things are real or integer numbers, right? That the machinery is very general since it works for Hilbert spaces. Right. I mean, can you say any more about that? Like, are people looking to see sort of what, there could be lots of features that are special to applying it in this situation. But I would have thought anyway that it wouldn't be sort of A's and A daggers, but more, number operators.
Yes. Okay. So let's talk about the number operators a little bit.
Yeah.
These guys. First of all, the A dagger A that is, the operators that you see here that are not number operators, not generally diagonal. The space that they're working on is a space of probabilities rather than a space of amplitudes, the way that it's normally applied. So that's kind of okay. But nevertheless, you might wonder, could we make special use of all the different number operators that you can build? And so you caught me with red hands. I'm trying to do that, but I don't quite have it yet, as a model reduction. So given a model that's like this for I mean, so think of it in the chemical reaction case, not the graph case. In the chemical reaction case, when we're doing those dynamical Boltzmann distributions, that is number operators. So at the fine scale, it's the master equation with off-diagonal stuff. And at the coarse scale, it's all number operators with coefficients that vary according to a differential equation. So you have to learn the dynamics for the coefficients in a number operator-like representation at the coarse scale. So I think that is a powerful way of proceeding, and you do get a kind of a model reduction that way. It's fundamentally simpler to be describing a time varying an operator that's a time varying weighted sum of number operators, and that's a useful statistical representation of your model.
Okay, thanks.
Should be a reduced one, yeah. But I haven't succeeded in doing it yet for the graph case. I mean,
yes, well,
there's formulas, but but in order to do it, you have to really have mastery of this thing here, and it's pretty recent.
Okay, thank you.
Yeah.
Any more questions? We had quite a few people not able to access. I'm not sure what happened. I suspect the link was re-forwarded, and some email client might have divided into 2 lines or one. I don't know what happened, but I had to resend the link, the same link, many times, and I spammed the list again. If well, one of the attendants, Corey, mentioned that the hyperlink was broken. So if there is any more info, I would appreciate, so we can avoid this problem in the future. But it was very nice. I enjoyed a lot. We will post this talk if Professor Mjolsness authorizes us. We'll send it to him first, and perhaps this
I'll
slide.
make sure I didn't say anything political, and then I hope that everybody will who couldn't see it before will be able to see it.
Yes, definitely, and the slides, if okay with you. All right, and I would like to repeat the call for posters for the October 26th event that Professor Mjolsness is organizing. We'll probably send you more information by email and try to put together, a nice gang of physical scientists to participate on this. All right.
And let me make one other announcement. So we're having our talks about every 3 weeks at the moment in the summer. But if anybody wants to suggest a speaker, we'd love to have them. Somebody who can say something that appeals broadly in the physical sciences is especially welcome, like we just heard from Eric. So please send me and Dominguez an email if you have a suggestion for someone to give one of these talks. We're going a little slower in the summer, and it'll heat up again once the fall starts. Okay.
Yeah. So I mentioned that Professor Penner replaced Roger McWilliams as an Associate Dean of Research and Innovation. Professor Kieron Burke replaced Roger as the head of the PSML Nexus effort. So they're probably both going to be pretty engaged into the effort.
Okay.
All
so
right.
let's thank Eric again.
Thanks, Eric.
Thanks, Eric. Yes.
I have one more question if there's time.
Sure.
Yeah.
The edges between the nodes in the graph, can they be like multi-dimensional, like a plane, or are they limited to just
So,
like as you increase dimensionality from like the 2D plane to more and more and more, can you have like complex connection points, or is it always just going to be line by line?
you could have any graph. These graphs are labeled on the nodes. If you were interested in edges between graphs that didn't play by those rules, for example, two nodes could have 16 edges between them, or they could have edges with labels on them. You can do all that too just by a computer science reduction from fancy labeled edges to bipartite graphs, in which you have node flavored nodes and edge flavored nodes. And then any labels that you had on your edges turn into labels on your edge flavored nodes. Think of them as red nodes and blue nodes, and you can never connect a blue node to, you can never connect straight from a color to itself. You have to go through the other color. And so it's just a straight translation, a straight reduction in computer science theory terms to the case that I described, which is labeled nodes and unlabeled edges, and any pair of nodes either has an edge or it doesn't. And so then so you make the labels do the work. Any kind of structure you want to put into your graph, you put it onto the node labels. And if you wanted edge labels, then you do this trick, and then you can have those too.
That's cool. Thank you.
Sure.
All right. So any last minute question? No, if not, feel free to put your facial coverings back. And hope to see you all soon.
All right.
Thank you.
Thank you.
Thank you, Eric.